All right. So the first thing I want to review, which we covered in Chem 1, was called the photoelectric effect. And Rutherford actually studied, I'm going to say, light and metals, and he found when light or energy of the right or necessary intensity is shined on metal, we will say electrons are emitted. That's what gives metal its shine. So it works when light is shined on it. It also works when energy is applied. I'm trying to think, and not really. Oh, Marissa, you could maybe talk about this. Do you have a farrier come out and work on your horses? Do you, any of your horses have shoes? So if he wants to form the shoe for the horse's foot, what does he do to it? Yeah, he heats it up until it's glowing, pretty much, right? And then he bends it or molds it to fit. That heating up when you to glow, like if you, how many of you have ever seen a farrier form a horseshoe? Anybody besides Marissa and myself? No? Oh man, how many of you have ever roasted a hot dog? Better success with that one. Have you put it on those metal forks? If you leave that, and this is a dumb thing boys would try to do, no offense boys, but I know you like to play with fire. Take that metal fork, and if you put it in that fire, or you could even do this on your kitchen stove, if you leave it on there long enough, what does it do? It glows. That glowing is really what we're talking about when we talk about the photoelectric effect. Somewhere. I printed out the picture. Yeah. So like here, there's the horseshoe. So when you get to this point where you're seeing this, where you're actually getting light from a metal object, that's the photoelectric effect. So that was one of the first things that made them start thinking about light and electrons. And then along comes the guy named Bohr, Niels Bohr, and he starts what we call the quantum mechanical model. And a whole bunch of guys work on this. He just starts it. Even Einstein worked on the quantum mechanical model. That's where his whole theory of relativity branches out from. So Bohr tells us some things. He says, or he figures out, that electrons are only found in specific paths, and he called those orbits. He says that each orbit has a fixed energy, and that is called an energy level. and those are both terms you should have heard before. Orbits are within energy levels. He also coined the term, which you should have heard before, quantum plural is quanta. And that is basically the energy required to move an electron from one level to the next. So to move it up. Because if you remember, or you should remember, that the way that we get light is by electrons moving up an energy level and then falling back down. Do you remember that? Remember that little diagram that we drew? Maybe we need to draw that again. So I want you to think about, I'm going to just draw, I'm going to pretend here, a couple protons. We'll just have a couple of electrons in this one. I'm going to run out of room. So the first thing you need to remember is the farther from the nucleus the farther apart the energy levels are. The closer to the nucleus, the more they're attracted to the nucleus because of this attraction. It's called effective nuclear charge. And think of that as how much pull the protons in the nucleus have on the electrons. So obviously the closer you are to the nucleus, the greater the pull of those protons. These electrons up here can feel the pull a lot more than when I get back here to the fourth energy level. So that's what keeps them closer to the nucleus, that effective nuclear charge. I'm going to let you get that, then I'm going to draw another one. Okay, we good on this one? You okay there, Chloe?
Yeah.
All right, so let's think about what happens. I'm going to stick with my helium here. Actually, I think I'm going to make this lithium. All right. So let's see what vocabulary you can remember. All right. If all my little electrons are happy and they're where they're supposed to be, what state do I call that when an electron is in the energy level it is supposed to be in? Anybody remember? Okay, so let's write that down first. It's called ground, bless you, ground state. And that is equal to the energy level that normally houses the electron. So now I'm going to come up here and I'm going to add some energy to this electron. Specifically, I'm going to add 1 quantum of energy. And that will cause that electron to go from its ground state up to the next energy level. So it jumps from ground state up to its next energy level when I add a quantum of energy to that electron. Do you remember what it's called when it jumps? Trey? Good. So when it gets up here, hey Trey, it's now in excited state. And we're going to say energy has been absorbed. Running out of room. This energy I add, it could be in the form of electricity like we're going to do with our gas discharge bulbs, or it could be in the form of heat like we're going to do with our Bunsen burners. Either way, we're adding energy. There's lots of different ways to do it. So I take my electron from ground state to excited state. On the way up, that electron absorbs that energy. It's called a quantum of energy. Then my electron falls back down to ground state. And I'm going to just draw an arrow and come over here and write so I've got some room. The electron falls back to ground state gives off energy in the form of light, and it's called 1 photon. Of light energy. So if it had jumped 2 levels, then it would give off 2 photons, or that would be 2 quanta. I only call it quantum when there's 1. If I made all of these guys jump, I would just add it up. Important terminology here. Quantum, excited state, ground state, photon. Okay. Take a second, come get one of these. So Mara, Lily, Kale, you guys will have to get one of these tomorrow when you come back. Oh, shoot. Here, somebody can have this one. I'll run a couple extra off. I thought I had plenty. It's okay. If I didn't get you one of those today, I will get you one tomorrow. If you look at that, you'll see the Roy G. Biv. We've seen that before. We use it for wavelength, frequency, all of those things. We have some formulas that you got before. When we work with light and electrons, I suppose now's as good a time as any to review those. All right, so let's review. We've kind of already reviewed how the light is made. But basically we can say it's called the dual wave particle theory of light. And it's really pretty simple. Like if you're asked to explain it, it can be done fairly simply. We say that light is caused by electrons which are subatomic particles. So there's where your particle part comes in. And that light energy that's caused by the electrons that's emitted or given off travels in waves. So there's your wave part. It's that simple. That's one of those short answer questions that a lot of times trips people up, but it really truly is. It's kind of a short answer. We don't get much farther into it than that. When we look at this light and energy, we had two basic formulas that we used. The first one was C equals lambda V. And the second one was E equals HV. Or really, when I say this, C is speed of light. Anybody remember the speed of light? No? No? 3 times 10 to the 8th meters per second. That upside down Y, that's a Greek letter. That's lambda. That represents wavelength, which is measured in meters. Speed of light was meters per second. And this fancy V looking thing is also a Greek letter, the Greek letter nu. And that stands for frequency. And it's measured in hertz, which is Hz, and that is basically waves per second, or 1/seconds. All right, on the second equation, Max Planck is the guy that came up with this one. And basically what he found was that he did a whole bunch of experimentation with light and kept track of lots of numbers and did lots of calculations. And basically he found that the energy of light divided by its frequency always equals a constant number. So it never changes. It's just like the speed of light. It's a constant, that h. And he called it, or it is called, because he discovered it, Planck's constant. And it basically looks like this. E over h is equal to frequency. Or in a straight line equation, it's E equals h nu. But when I use this E over A, or this V is equal to E over H, or E over H, E equals H nu, they're all the same formulas. I mean, I can also take this, and if I really want to prove what Planck said, I can take my H equals E over nu, and here's where I always get the same number. And that would equal Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. So E here is energy. Energy is measured in joules. It's a capital J. Nu is frequency. Which is hertz. Which is waves per second. And then that H is Planck's constant. The value's right there. Okay, so those are some things you're probably going to have to commit to memory. the speed of light, Planck's constant, and those two formulas. But let's put, like, these are real, this is like really simple math. You'll like this to begin with. There's not a lot of thought to it. It's just, they're just straightforward questions like, I'm just going to give you maybe 3 examples. Calculate the wavelength of light that has a frequency of 3.28 times 10 to the 12th hertz. So there's the first one. Figure out what formula to use out of those two. Write down your variables, plug stuff in, and see, but I really want you to write down your work. Like, think it through these first couple of times, even though it's super easy. Pull out your calculator. So is it pretty obvious which formula you're going to use? Should be. All right. Oh, let's see. Grace, what'd you get for an answer? 9.15 times 10 to the negative what? And what would my units be on that? What? Meters. Hertz cancels out seconds because remember hertz is just like 1 over seconds. Did you like that problem? Yeah. There's not 19 steps. Let's try another one. Calculate the frequency of light with an energy of 4.5 times 10 to the 11th joules times seconds. using my calculator. Logan, what'd you get for an answer? Did you get one? Times 10 to the what? 44th hertz. You guys agree with him? Okay, so let me give you one. That is, at least you have to think about it a little bit more. Let's say a certain light has an energy of 7.92 times 10 to the 12th joules. What is its wavelength? Feel like you know what you're doing? Did you get an answer? Your calculator died? You want a calculator? I don't know where mine is. Here's one. Do we have an answer? Raise your hand if you have an answer. Okay, a couple people still working. I'll wait just a minute or two longer. Kaylee, what'd you get?
2.5 times 10 to the negative 38.
We're solving for wavelength. What would my units be? All right, be honest. Raise your hand if you got that. Yay. Okay, let's have a little break. Then we'll come back. I have another job for you to do.